Here's the right one. So I got to share the screen somehow. So, okay, I hope you guys at home can hear and see this. Everybody at home okay? Can you hear and see what's going on here, the green screen? Fantastic, thank you. Let me know when you need something. Yep. So I want to spend this morning getting organized to see what's going on with what we've done last week. Then we've got another test of series to see if series converge or diverge. So one of the things that we've got to learn how to do is not just decide whether a series converges or diverges, but explain to me why you come to that conclusion. Tell me what test you're using. Tell me the steps in the test. Don't just stop in the middle of the test and assume that I know what's going on. I do know what's going on. I want to make sure you do know what's going on. So make sure that you say this series converges because the integral converges or something like that. Make sure you state a conclusion and don't make me guess what's going on. So here's what we have so far. We started with a series, and all of the series that we're talking about, other than the geometric or positive term series, and a subtelescoping series. So what we have so far is one of the very first things that we did was that if the sequence of partial sums oh, great. Yeah, what's going on with that? System error. Oh, thank you. So, who? Okay, so what do I do when that does that? Close it, maybe? Oh, that's the Zoom. Load that bad boy. Cross your fingers. Let's let you guys watch the little circle and get hypnotized. Not working. Those old pepper cam. Sharing has stopped. Well, that's stupid. There we go. It's back. I'm going to go back to screen share. Maybe. Okay, screen share. Down there. Down there. Okay. going back. I get record again. I think I'm going to try camera record. Screen record has screwed me up. Let's try that. Okay, so one of the things that we were talking about in showing convergence of a series is if it's possible to write the partial sums in closed form as a formula for what the nth partial sum is. Then we've got a sequence of partial sums. The nth partial sum is just the sum from k is equal to 1 to n. So it's A1 plus A2 plus A3 out to AN. Now, if we can get that pattern recognized, maybe if it's a telescoping series or geometric series, if we can write that as a closed form, some formula without the plus dot, 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 then if this sequence has a limit, then the sequence converges. If the sequence converges, then so does the series. And it converges to the same thing. So we look to take the limit as n goes to infinity of that general term, and we get some sort of sum. And if this does happen, then that sum is the same as the sum of the series to infinity. But this is kind of hard to do. Like I said, maybe the only time you can do this is if you have a telescoping series. So we look for that. It's kind of a, you can kind of smell them out by now, I hope. One special type of telescoping series that I was able to manipulate the partial sums for was a geometric series. So another type that we have so far is a geometric series. It would have the form A plus AR plus AR squared on forever. We can write that from K is equal to either 0 or 1, I don't care, I'll start it at 0, and then you have A, R to the K. If you have that particular type of series, we know that it converges if that multiplier from one term to the next in absolute value is smaller than 1. And we know what it converges to. It converges to the sum S is equal to A over 1 minus R. That was in section 8.2. In section 8.3, we had the integral test. This is restricted to positive term series only. The integral test said that if your nth term of your series corresponds to a function that is continuous and decreasing and passes through each of those components. What's wrong? Oh, if you have the function that passes through, I don't like this little window looking at me, that's kind of freaking me out. I'm not talking. Now I am talking. Okay. If you have an integral that passes through the points generated by the series, if the integral converges, then so does the series. If the integral diverges, then so does the series. So we've got some sort of continuous, decreasing function f of x that contains the points A1, A2 forever. Then The series does whatever the integral does. If the integral converges, so does the series. If the integral diverges, so does the series. And one special category of series that's easy to see when it converges by looking at the integral test was a p-series. A p-series had the form, the counter is in the denominator, and it's raised to a power. Through the integral test, we proved that the p-series will converge if that power on k in the denominator is strictly bigger than 1. It diverges for p is equal to 1 and diverges for p less than 1. Then we also had a series that looked a lot like a p-series called a q-log series. That we looked at using the integral test. A q-log series has a logarithm in the numerator and then k to a power in the denominator. This time I'll use a q as the power. The q-log series converges in much the same way that the p-series does, where that power q is strictly larger than 1. It can be shown, that property can be shown using the integral test. The only problem is the integral has to be computed by parts, and it can get kind of messy after a while. So if we just kind of remember that it follows the behavior of a p-series, I think it makes life easier on you. We had also the test for divergence. Which is not a test for convergence. It's only a test for divergence. It is related to the integral test. In order for an improper integral to infinity to converge, the graph has to hug the x-axis closely enough. That will only happen if the nth term of your series has a limit of 0. If the nth term is not 0, then the integral has no way of converging. And so the test for divergence says that if you take the limit as, I'll use a k again, k goes to infinity, for the general term of your series is not 0, then the series diverges. If the limit is equal to 0, then we don't know anything. We know absolutely nothing. It's possible for a series whose kth term goes to 0 to converge, but it's also possible for those types of series to diverge. For example, the harmonic series, 1 over k, from k is equal to 1 to infinity, is a divergent p-series, but 1 over k goes to 0 as k goes to infinity. So even though it decreases where its kth term goes to 0, it is a divergent series. So be careful. Don't use it as a test for convergence. It's only a way to quickly eliminate divergent series. Then we had 2 comparison tests. We had the direct comparison test. And I'm using A's to be the series that we're testing. There were two parts to this. If you found a lookalike series that converged, and our given series had terms that were all smaller than the terms of the convergent series, then our series converges. If your lookalike series diverges, and all of our terms are bigger than the terms of the divergent series, then our series diverges. So we pick a lookalike series. Let's call those the BKs. If the AKs are smaller than the BKs, for K big enough, and the lookalike series converges, then our series converges. It's easier to say that a series that is smaller than a convergent series is convergent. It's easier to remember it that way. The other case of this test was if the AKs were larger than the BKs and the BKs diverge, then the AKs diverge. Which we say as bigger than divergent is divergent. That's the direct comparison test, and I'll abbreviate that DCT. The only problem with the direct comparison test is if you're comparing your AKs to the BKs and BKs converge, but AKs not smaller than the BKs, then you can't use this. If these inequalities go the wrong way for the type of series you're comparing it to, then you don't want to use this test. Perhaps an easier, quicker test to use is called the limit comparison test. We start the same way. We pick a lookalike series by throwing away the insignificant terms. But then we take the limit as k goes to infinity of your series over the lookalike series. If that limit is a positive finite number, then both series do the same thing. So this limit indicates that they're kind of floating along at the same rate. So if they float along at the same rate and the BKs converge, then the AKs will follow. If they float along at the same rate and the BKs diverge, then sure enough, the AKs follow that as well. Okay. And we'll denote that, the limit comparison test. The two cases linked to this one, if L is not positive, in other words, it could be 0, then there's a case for that. And if L is infinite, then there's a case for that. So let's list that now. That's where I ended last time. That'll be the zero infinity case of the limit comparison test. You set up the same ratio here. If that limit L is 0 and your lookalike series converges, then so does the series that we're testing. If your limit is infinite, and your lookalike series diverges, then so does the series you're testing. But if the limit is 0 and the BKs diverge, you know nothing. If the limit is infinity and the BKs converge, you know nothing. So it has to follow this to a T. One of the hardest things about using these tests is knowing the tests. You've got to know exactly what each test says. So it would help if you kind of kept a referral sheet next to you when you're doing homework, where all of your tests have the what ifs on them. Then we're going to kind of try to look at today, which test should we use for which conditions. It's easy to see when a series is a p-series or a geometric series, if you've practiced with them enough. Those kind of jump out at you. It's a little bit harder for some of us to see what we can integrate. And integration a lot of times takes more steps than's worth. So I put the integral test kind of way down the line on my preference of tests. Mostly things that I can integrate are obvious to me, like e's to a power and that kind of thing. The comparison tests work really well for things that are almost things that are geometric series, but maybe they're off by a term or two. Or they're almost a p-series, but they're off by a term or two. Or they're almost something that I can integrate, but they're off by a term or two. That's when I jump to a comparison test. I very rarely try to show that a series converges by the sequence of partial sums because it's hard to write the nth term unless the series obviously has that property. Or there's only two series that when we show that it converges, we can find the sum. So if I ask you, show the series converges and find its sum, then that's kind of a hint. It's either a geometric series or a telescoping series. Those are the only two that you can find the sum of. That you can find the sum of. Otherwise, we need to have other techniques that we're not going to see in this class. And so, I've got a bunch of examples.
Kind of sounds like we did a note card.
A note card while you're preparing, while you're doing homework, while you're studying. But after a while, that has to be up in here. That's the neat thing about being in mathematics or science or engineering. You're developing your step-by-step process of what it is that you need to do in your everyday life. And so that's why I think you need to have things in your head. Can't have a step-by-step process if you don't even have any steps. So it's got to be there, sitting there in your head. And how scary would that be? For instance, you go to your doctor and you list your symptoms, and your doctor pulls out a note card and says, nope, not that. Not that. Maybe. That would kind of freak me out. I want my doctor to have answers.
They probably do that when they leave the room.
Well, that's fine. You can use your note card when you leave the room. Keep it fresh. Okay, so here are some examples. Whew, it's hot up here. Okay, let's see, can you see that? Okay, so determine if the given series converges or diverges. Clearly state what test you're using. If a series converges, can you find its sum? And as a side note, you can only do this if the series is geometric or telescoping. Here's my first one. Sometimes I'll write the general term with an N, sometimes with a K. It's okay. Don't be bothered with which one I use. Let's get used to both. So I wrote for you the series whose terms look like n squared over n times n plus 3. So it's clearly not a geometric or a p-series. A geometric series has a ratio, a constant, and the counter is the power. A p-series has it the other way, has a constant on top and the counter to a power on the bottom, a numerical power. So I've got an n on the top and n on the bottom, so it's neither geometric nor a p-series. So if it's not those, if those don't immediately jump out at you, the next thing I want you to look for is to make sure that it has a chance of converging. Does the limit of the general term go to 0? This one does not, right? We're doing our test for divergence. You take the limit. Here is n goes to infinity of n squared over n times n plus 3. If you multiply out the denominator, either in your head or on paper, you see that the degree on top is the same as the degree on the bottom, so that limit is not 0. What is this limit in this case? It's 1. And since that's not 0, the series diverges. Okay, so there's my statement of the test. Here's the performance of the test. Here's my conclusion. That's the thing that I'm looking for you. Let me know what it is you're doing, how you're doing it, and what you decide. Okay, so let's take the n squared off of the top. And now look at the same series, but put a 1 up there maybe. Now the degree on the bottom is bigger than the degree on top, so the limit does go to 0, so it has a chance of converging. It also has a chance of diverging. It also looks like something that when we were integrating, we would integrate by partial fractions. So I don't plan on integrating this, but I do plan on doing the partial fraction decomposition, because if one of the terms has a minus sign, it's possible that this is a telescoping series, and I can decide whether it converges and find its sum. So I'm going to do the partial fraction decomposition to see if it's telescoping. Okay, so let's rewrite 1 over n plus 3 as something over n plus something over n plus 3. I'm checking to see if this is a telescoping series. So I cross multiply and I get 1 is equal to a times n plus 3 plus b times n. And if I let n equal 0, then the b term is gone, and I have 1 is equal to 3a, so a is equal to 1/3. If I let n equal negative 3, then the a term is gone, and I get 1 is equal to negative 3 times b. So b is a negative 1/3. And now I want to look at the terms in the series when it's written in its partial fraction form. I'm going to have a 1/3 over n. Let me just put that 1 over 3n. And then this minus sign here, I can write like this. Now let's look at the sequence of partial sums. Let's look at the nth partial sum. Actually, I used an n up here, so let me use a capital N down here. So I'm going to write out the terms from n is equal to 1 to capital N. When n is 1, I have 1/3 minus, let's see, n is 1, that's a 4. 3 times 4 is 12. When n is 2, when n is 2, I have 1/6. 2 plus 3 is 5. I get minus 1 over 15. When n is 4, I have 1/12. 4 plus 3 is 7. 3 times 7 is 21. I don't know. Did I skip 3? Yeah. So that'd be a 9. Three times 3 is 9. 3 plus 3 is 6. 3 times 6 is 18. All right. N is 4. I have 1 over 12 minus 7, 1 over 21. That's the first term that's going to add something out. Let's keep plugging. That's n is 4. Now n is 5. I get a 1 over 15. 8, 3 times 8 is 24. Geez, if this is telescoping, it's taking its sweet little time. I got that out. I got that out. N is 6. 3 times 6 is 18. And and n is 6, 9. 3 times 9 is 27. Good gosh. So I've lost these two. Lost these two. I don't think I like the way this is panning out. It doesn't look like it's a nice, perfectly telescoping series. Okay, so not obviously telescoping. So my other choice then is to either do an integral test or one of my comparison tests. Like I said, integral test is not too enjoyable, so I'm going to do a comparison test. I'll decide which comparison test I do as I do it. So I'm going to go back to here, and I'm going to compare to the series. Well, I keep the one on top and just get rid of the 3n. That's not as big as the n squared. So I'm comparing it to 1 over n squared. What do you know about the series 1 over n squared? It's a p-series where p is bigger than 1. This is a convergent p-series. I can do the direct comparison test because it's easy to see that my AKs are smaller than my BKs. At least it is to me. So I'm doing the direct comparison test. I take the denominator from my AKs and multiply it out, and it looks like n squared plus 3n. That's larger than the denominator for my BKs by 3n for each n. Now my series has those in the denominator, so I'm going to flip both sides of this. But when you flip both sides, that flips the direction of the inequality. So the terms in the series that I'm testing are smaller than the terms in a convergent series. Smaller than convergent is convergent. So I'm comparing, I name my test, I check the sizes, and I tell you what my comparison series does, and then I make my conclusion. Okay. Comparison tests work really well if you've almost got a p-series. I was off by this 3 here. So ditch it, and then compare it to the p-series.
So then why do all the telescoping stuff?
Because I might be able to find the sum, right? If there's a chance of finding the sum, I'd kind of like to do it. And I've seen terms that look like that did telescope easily. And this one still might if I wrote out enough terms. I just lost patience with it. All right, here's you another one. The sum from n is equal to 0 to infinity of 5 to the minus n power. Well, when I see that, I see the minus n power. Automatically, my algebra kicks in, and I want to write that with positive exponents. So let's replace 5 to the minus n with 1 over 5 to the n. Now, does that make you think of anything? What do those terms look like if you wrote out, say, the first 4 or 5 terms? It does look like geometric. Take a look at it. If n is 0, I get 1. If n is 1, I get 1/5. When n is 2, I get 1/25. So it has the right form for a geometric. I progress from one term to the other by constantly multiplying, in this example, by 1/5. So this is a geometric series with r is equal to 1/5. In the geometric series, we compare the size of the multiplier to 1. As long as the multiplier is smaller than 1, it converges. And we know what it converges to. First term divided by 1 minus r. The first term depends on what the counter starts at. R started at 0, so our first term is a 1. R is 1/5. So ours converges to 1 over 1 minus 1/5. That puts a 4/5 in the denominator. 1 divided by 4/5 is 5/4. We got a geometric series, it converges, and for a geometric series, we can find the sum. So how about the sum from n is equal to 2 to infinity of e to the 3 minus 2n. What are your thoughts here? It is also geometric. You kind of recognize it because e's a number just like 5 was. You've got a numerical base. You should have your little radar up, feeling out the geometric series. Let's write out the first few terms so that we know what a and r are in this case. My counter starts at 2. So when n is 2, I have 3 minus 4. 3 minus 4 gives me e to the negative 1. When n is 3, I have 3 minus 6, so I get e to the minus 3. When n is 4, I have 3 minus 8, I get e to the minus 5. Looks like I'm getting all the odd powers on e. So there's my first term, 1 over e. What's r? 1 over e squared. Is that number bigger or smaller than 1? Much smaller than 1. E is about 3, so this is about 1/9. It's smaller than 1, so it is a convergent geometric series. If it's a convergent geometric series, we know its sum. The sum is a over 1 minus r. We decided a was 1 over e, and r was 1 over e squared. You can leave it like that, or you can clean it up a little bit by multiplying top and bottom by e squared. If you multiply top and bottom of that by e squared, you won't have those fractions laying around, and you can write your sum as e over e squared minus 1. Any questions? Feeling okay? Then 5 then. Let's look at a numerator that has 9 to the n plus 2 to the n divided by 5 to the n. What would happen if you do take the limit as n goes to infinity? The top grows faster because 9 to the n grows faster than 5 to the n. So by the test for divergence, this term does not go to 0, and so the series diverges. Perfect. You can also look at it like this. I can break that up by breaking up the numerator as 9 to the n over 5 to the n plus 2 to the n over 5 to the n. And that would be then the sum of two geometric series, 9/5 to the n plus 2/5 to the n. 9/5 to the n is a geometric series where r is bigger than 1, so it diverges. 2/5 to the n is a series where r is smaller than 1, and it converges. But do you remember that we said that if you had the sum of a divergent piece with a convergent piece, then that sum is going to follow the divergent piece. Divergent plus convergent is divergent. But I'm very happy that you saw the test for divergence. I'm just as happy with that. Okay, number 6. Sum from k is equal to 1 to infinity of 1,000 over the square root of k.
Well, that's k to the 1/2.
That is k to the 1/2.
You can take out 1,000.
You can take out the 1,000. Don't worry about the 1,000 one bit. So what does the k to the 1/2 tell you?
P is less than 1.
That is a p series. P is smaller than 1, and our conclusion? Diverges. Very good. Very good. See, it's a quickie. When the power is a number and the base is the counter, it's a p series. When the power is the variable, the counter, and the base is a number, then it's geometric series. Okay, sum from k is equal to 1 to infinity, k divided by k squared plus 1 to the 3/2 power.
This also be a P series?
It's not a p series because I have a k on top and a k on the bottom with a plus 1. So it's not quite a p series. If that plus 1 were gone, we could simplify it to a p series.
And did you do a comparison?
Then you can do a comparison test. If it's not quite a p series, you can compare. Okay, so let's start this with a comparison test. All I'm going to do is throw away that 1. That's what screwed us up from not being a p series. So I'm going to keep the k here, I'm going to keep the k squared here to the 3/2. And then I'm going to simplify that. What is k squared to the 3/2 reduced to? K cubed, so I have k over k cubed, which simplifies to 1 over k squared. Now we have a nice p series. P is 2, bigger than 1, so it's a convergent p series. I can do the direct comparison test because when I formed my BK series, all I did was throw a 1 away from the denominator. So if I threw a 1 away from the denominator, the original series has a bigger denominator and the same numerator. So the original series is going to be smaller. It's divided by something bigger. K divided by k squared plus 1 to the 3/2 is smaller than k divided by k squared to the 3/2. So we have, by the direct comparison test, smaller than convergent is convergent. Did anybody look at this original series and get the hankering to integrate? It looks like things that we integrated. If you put an x on top and an x squared plus 1 to a power on the bottom, it does look like something we can integrate. So we could also do the integral test. And since we can do it, I'm going to do it. It is that easy. I just want to convince you that comparison tests are really easy. Okay? But some of your web work problems are structured in such a way that say, compute this improper integral, then make a conclusion about this series. So you it forces you into doing the integral test. So just for fun, and hey, isn't that why we're all here, is just for fun? Or to get a degree, whichever the case may be. We'll do this another way using the integral test. We consider the function that looks just like this, but now let's write it as a function of x. So I've got a continuous function because I never divide by 0. It does have a square root in it, but that's okay. It's continuous for all values of x. I need to verify that it's decreasing. And I kind of like using the derivative to show that it's decreasing. So I'm asking myself, is it decreasing? I look at the derivative, which is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Don't forget that old chain rule when you take the derivative of the bottom. That's where I got that 2x. When I simplify this, I'll have an x squared plus 1 to the 3/2 here. That 2 cancels that 2, so I have a 3x squared times an x squared plus 1 to the 1/2. And downstairs we have an x squared plus 1 cubed. There's a common factor of x squared plus 1 to the 1/2. So I'm going to take it out here. To take half out here, that leaves me 2 over 2. So this becomes a first power. Take a half out of here. 3 minus a half leaves me 2.5, which is 5/2 there. Since this is now to the first power, and this is gone, I can take my x squared minus 3x squared and get a negative 2x squared plus 1 as my numerator. I can simplify it to that. The numerator is 0 when x is the square root of a half. So as long as I choose x is bigger than the square root of a half, let me see what the sign of f prime is. Like, let's put in a 10 for x. If x is 10, that's going to be 100, negative 200. That's a big negative number on top, positive number on the bottom. So when x is big enough, it decreases. I have a decreasing function. Modeling this series, I compute the improper integral to infinity. Whatever the integral does, the series does. Spoiler alert, we know the series converges, so my integral better converge. And so, we compute the integral from 1 to infinity of x over x squared plus 1 to the 3/2 power. That's your run-of-the-mill u du integral, because the degree on the bottom is 1 more than the degree on top. So I'm going to take u to be x squared plus 1. And du is 2x dx, so 1/2 du is the x dx. And we can rewrite our integral then with a 1/2 out front. 1 over u to the 3/2 du, which is a u to the negative 3/2. Add 1 to the power, divide by the new power. When I add 1 to the power, I get u to the negative 1/2, so that puts a negative 2 out front. And we get negative 1 over u to the 1/2, which is the square root of u. U is x squared plus 1. And we're going to evaluate that from 1 to infinity. So now let me kind of write it nicer. N's going to go to infinity. We have negative 1 over the square root of n squared plus 1 under the radical sign. Minus a minus gives me plus 1 over the square root of 2. And as n goes to infinity, this term has an n in the denominator, constant in the numerator, and so that term is going to go to 0. My integral converges to 1 over root 2. And so here's my conclusion. The integral converges, and so does the series. They don't converge to the same number. Very rarely does that happen. Usually the integral has a little bit more to it. So I can't use that 1 over square root of 2 other than an indicator that the integral converges. So I know by the integral test, the series will then converge.
When you were trying to find out if the integral was, if the function was decreasing, could you kind of just think that it is decreasing because the bottom is getting bigger? Does that make sense?
Yeah, that does make sense. This behaves like 1 over x squared, and I know that decreases.
Okay.
But I got all this calculus in my head. I could use it sometime, right? I gotta just pour it out. Why not use it in the calculus class? But you're right, I did that to almost convince you that we can do a comparison test in 3 lines and an integral test in more than 3 lines, even though this was something really easy to integrate. So an integral test is probably a last-ditch kind of test because the other ones are so much prettier and quicker. Unless you're into that kind of thing. I don't want it pretty and quick, I want it dirty. All right, that's example 7. How about example 8? That would come after example 7, would it not? Let's take the sum from k is equal to 2 to infinity of 1 over k times the natural log of k squared. Now, just because it has a logarithm in it doesn't mean it's a Q-log. The Q-log series has a logarithm in the numerator and k to a power in the denominator. The logarithm in the denominator is not a Q-log series. Almost, but it ain't. All the k's are in the denominator, so it doesn't, the test for divergence doesn't help me any. Always eyeball your series to make sure the limit goes to 0. So armed with all of your tests, which one would you like to attempt right here?
Geometric?
It's not geometric because in the geometric series, the base is a number and the power is the counter. Yes?
If we compare this to 1 over 2k, since the natural log of k increases so slowly,
2k, why 2k?
the log rule, oh wait, no.
That whole logarithm is to a power. But you're right, think in our tower of power. In our tower of power, the logarithm's way down here, and any other power of k is above it. Like that, right? So I can use a comparison test and say compare the natural log of k to the square root of k. And so I can choose my BK series to, instead of having a natural log of k down there, put the square root of k down there. And the square root of k squared is just k, so my BK series is a P series. This is a convergent P series. P is 2, which is bigger than 1. Okay, now let's look at the size. I compared the natural log of k as being smaller than the square root of k. And since those are both positive numbers, the natural log of k squared is smaller than the square root of k squared. And then if I multiply them by k, they're still smaller in that direction. But now if I flip, it flips the direction of the inequality. So I don't have the direct comparison test. The series I'm using as my comparison series isn't above the series that I'm comparing it to. I don't have smaller than convergent. I have bigger than convergent. So if that happens, then I can do the limit comparison test. Okay, so we can't use the direct comparison test. So we use the limit comparison test. We take the limit as k goes to infinity of our given series divided by our lookalike series. So I take my 1 over k, natural log of k squared, and divide it by 1 over k squared. Right, that's what my series simplified to. Now I'm going to flip and multiply. That puts the k squared on top. One of the k's will cancel, And so I need to take the limit as k goes to infinity of k divided by the natural log of k. It canceled right here. Yeah, I got an ln of k squared. Well, that looks like to me infinity over infinity, right? I don't know how ln of k squared grows, but let's do L'Hopital's rule. So we get the limit as k goes to infinity. Derivative of k is 1. The derivative downstairs is 2 times the natural log of k times 1 over k. So that's the limit as k goes to infinity. That k jumps out on top, and I have 2 natural log of k here. What do you know about that limit? The top is bigger, which means this limit is not a positive finite number. My limit is infinite. Go to the zero infinity case of the limit comparison test. The zero infinity case of the limit comparison test says, where's my first page? If the limit is infinite and the bk diverges, then so does the ak. Well, dang it all to heck, our bk's were convergent p-series. So it's not the infinity case of the limit comparison test. So the direct comparison test had the directions going the wrong way. Couldn't use that. The limit comparison test has the wrong limit and convergent bk's. Can't use that. So both my comparison tests did not work for this particular example. Got another choice? Integral. This is what logarithms are easy to integrate, especially this is a 1 over u du integral. Take u to be the natural log of k and du is 1 over k. The integral test in this particular example is the quicker test. All the k's are in the denominator, so you can eyeball it and see that this is a decreasing function. The numerator is a constant. Both terms in the denominator grow. So we're going to do the integral test. Both of these failed. So we're going to do the integral test. Take our function to be 1 over x, ln of x all squared. And we know it's continuous on the interval from 2 to infinity and decreasing. So now all we're going to do is integrate it from 2 to infinity. So take u to be the natural log in the parentheses. Du is the 1 over x term. And so we're integrating 1 over u squared. What's the integral of 1 over u squared? Negative 1 over u. So I'm going to take the limit as big N goes to infinity of negative 1 over the natural log of x from 2 to n. So that's the limit as big N goes to infinity of negative 1 over natural log of n. Minus a minus gives me plus 1 over the natural log of 2. Negative 1 over the natural log of n is going to go to 0 as n goes to infinity because the n is in the bottom. So I get 0 plus the natural log of 2, which is a constant. The integral converges, so the series converges. So this was a nice example to show you that don't shy completely away from the integral test. And it's not hard. I like to use the integral test when I have a logarithm in the denominator. But you'll develop your likes and dislikes by doing more and more and more of these.
But that doesn't mean that the series converges to the natural.
Correct. Probably doesn't. Because remember, the integral gives you the entire area under the curve. When we're looking at a series, then we've got these little sticks added together. So you're essentially adding boxes of width 1. And this, not even quite that much. So usually the integral contains more unless we've got something that does a little flipping around initially. Okay, so here's a near cousin of this. One more. Got one more here, and then we'll start something new. Let's go from the sum. Let me see. N is equal to 2 to the infinity, 1 over the square root of n plus the natural log of n. I'm going to ask you to see if you can use the limit comparison test on this. So you can form your lookalike series either by just throwing away the insignificant term there. Which term in the denominator is less significant? The natural log. You can just throw it away, or you can replace it with the square root of n. Either way, it's going to work out the same way. All right, so if you don't want to make a big jump to a lookalike series, I can pick my BKs or my BNs. Just drop the natural log of n and replace it with the square root of n. So you get 1 over 2 square root of n. I said use the limit comparison test because this BK or BN term, does it converge or diverge? What kind of series is this? It's a P series where P is a half. Does it converge or diverge? Divergence. This is a divergent P series. And my series is smaller than that one. Is it? Or bigger than that one? I don't know. Who wants to use the direct comparison test anyway? I asked you to use the limit comparison test. Take the limit of the given series over your lookalike series. And if you get a positive finite number, they both do the same. When you divide one fraction by another, you flip the one on the bottom over, which puts 2 square root of n on top. And we can evaluate that limit by looking at the highest power on the n. We decided the square root is a higher power than a natural log, so they both behave according to a square root of n. What will this limit then be? 2. This limit is 2. This highest power on n. I get a positive finite limit. The limit comparison test says that both series will do the same thing. So I go back up here and I look at my comparison series. It diverges. So our series diverges by the limit comparison test.
But if you didn't replace the natural log of n with your decay, you get the limit would be 1.
The limit would be 1, still a positive finite number. So there's no big whoop in whether we did that or not. Okay, I think I probably need to stop reviewing the tests we have and jump to our brand new, never been used test. These comparison tests work really well when you've got n to a power divided by n to a power terms, where the power is either a whole number or a fractional exponent. Those are fantastic. Or you can compare things that we know how they behave in the long run. But we sometimes encounter series that have factorials in it. Let me see if you know what a factorial is. On page 5. Let me find some more paper here. You guys are working me hard today. Working me hard. How much hard am I going to work? About 2 pages more? All right. We're in section 8.5 now. We'll get 2 more tests. We're going to get something called the ratio test. And then there's also a test called the root test. And both of these, or at least the ratio test in particular, are good when the series contains factorials. Because factorials tend to cancel nicely. Other things that tend to cancel nicely are products to the nth power. Doesn't have to be the nth power, could be any power, but the nth power is usually a giveaway. So what is a factorial? When you see the number 5 with an exclamation point, you read that as 5 factorial. A factor. There are 5 factors in 5 factorial. What are the 5 factors? 5 times 4 times 3 times 2 times 1. You came up with this?
Yeah.
Oh no, I wasn't there. It might be old, but I wasn't there when they came up with this. We probably saw factorials for the first time when you were studying counting techniques. In how many ways can you rank 5 dogs in a beautiful dog contest? Right? So there's 5 ways to pick the first place dog, 4 ways to pick the second place dog, 3 ways, 2 ways, then 1 way. So 5 times 4 times 3 times 2 times 1 is 120 different ways to put 5 dogs in ranked order. That's probably where you first saw that. So factorials arise in counting, in permutations and things like that. So when we have n factorial or k factorial, either one, then I can write that as n times n minus 1 times n minus 2, and I keep decreasing it until I get down to times 1. And so if I had, for instance, n factorial divided by, say, n minus 2 factorial, then I can algebraically reduce that. N factorial is what I just wrote. N times n minus 1 times n minus 2, all the way down to times 1. So n minus 2 factorial would start with n minus 2, then multiply with n minus 3, n minus 4, all the way down to 1. And there's a lot of common factors in the numerator and the denominator. So I should be able to cancel my factors that are common. There's going to be an n minus 2. Right next to this one would be an n minus 3. All of these guys in the dot, dot, dots are gone. And we're left with n times n minus 1. So we're going to be doing stuff like that in the ratio test. And here's the ratio test. Let an, from n is equal to whatever to infinity, be a positive term series. We're adding a bunch of positive numbers together. Though we will see in about a section that that's not that important. We're going to have a version of the ratio test that looks at the terms in absolute value. But for a positive term series, we don't need absolute values. Suppose that the limit as n goes to infinity of the an plus 1 divided by the an series is a number L. In other words, an plus 1 is the series where, in its general formula, each n is replaced by n plus 1. Then divide it by the general formula as it sits. Take that limit and get a number L. The size of that number determines if the series converges. If L is smaller than 1, then the series converges. Think of it this way. If this is your series A1, A2, A3, A4, out here somewhere you're at AN, right next to it is AN plus 1. So if I take the previous term and divide it by the next term and get something smaller than 1, then they're getting smaller fast enough to converge. If it goes the other way, if L is bigger than 1, then this guy, the next term, is growing faster than the bottom, and so the series diverges. And this would be the perfect test, except there are cases where L is equal to 1, in which case this test gives you no information. You've got to try something else. If L is equal to 1, then we know nothing. Try something else. What you'll find is you'll get a limit of 1 in the cases where a comparison test works better. We don't have factorials. We don't have n powers. Things don't cancel nicely. So you end up making a fraction where the degree on top is the same as the degree on the bottom. So look for factorials and nth powers. And then this ratio test, which I better write it over here, the ratio test. It's pretty easy to use. It's going to become your favorite test. You're going to try to use it on everything. But again, it doesn't work on everything. Just look for the giveaway factorials and nth powers, things that are usually multiplied together. Doesn't work when things are added together so well, right? Because you can't cancel through a sum, you can only cancel things through a product. And we're hoping to get a lot of cancellation occur right here so that we can get a limit L. So let's look at my first example. So the question will be converge or diverge. Let's see. I used n's up there. Let's take 2 to the n and divide it by n factorial. So just think of your tower of power. Which one grows faster? A number to the n or an n factorial? N factorial is way up at the top of your tower of power. It might be underneath n to the n, or it might be somewhere near there. But n factorials are faster growing. So this does have a limit that goes to 0, which means we don't know anything other than to try something. I see the factorial in the n power. Hey, why don't we try our brand new, never been used ratio test? Okay, so that's what the giveaway is, the factorial, the nth powers. So we're going to try the ratio test. Where we take the limit as n goes to infinity of an plus 1 divided by an. In the next section or two, we'll look at the absolute value of that ratio. When terms are not all positive, we just put it in absolute value, and the same conclusions hold. Now, I'm going to go up to this series and form the an plus first term by replacing each n by n plus 1. So an plus 1 simply looks like 2 to the n plus 1 divided by n plus 1 quantity factorial. Then you divide that by the series that we started with, which was 2 to the n divided by n factorial. In the next line, I'm going to take the 2 to the n over n factorial, flip it over, and multiply. Now, to help you see how things are going to cancel, I'm going to rewrite this next line. I'm going to write 2 to the n plus 1 as 2 to the n times 2 to the 1. Let me see if you believe that I'm allowed to do that. You agree that that's the same as that? 2 to the n times 2 to the 1 without that 2 jumping up so high? You multiply like bases, you add exponents. So if I have something with added exponents, I can multiply like bases. Then I've got the n factorial up here. Then I've got the n plus 1 factorial. And I'm going to write n plus 1 factorial as n plus 1 times n factorial. Does that make sense to you? N plus 1 factorial is n plus 1 times n minus 1, blah, blah, blah. And all that back here is n factorial. Then I've got, let's see, so that's the n plus 1 factorial, then I got 2 to the n. And now I can see easily what cancels. The n factorials cancel, the 2 to the n's cancel. This term knocks out that one. These two guys cancel, and we have this limit left. I just have a 2 to the first power on top and an n plus 1 on the bottom. Quick, what's that limit? 0. So we go up here to our cases. There were 3 cases. If the limit's smaller than 1, then our conclusion is our series converges. Okay? So I state my test. I tell you how I'm going to perform my test. Then I do it. And then I state my conclusion. I want you guys to get in the practice of doing that. Okay, here's another one. Let's just put factorials all over the place. Let's take the quantity 2k and put it in the numerator. Let's stick with n's. 2n in parentheses factorial. And in the denominator, let's put n factorial squared. I can. Maybe. There it is. What's 0 factorial? 0 factorial by definition is 1. It's the number of ways to put 0 items in a row. And there's only one way to do it. Boom, I just did it. Right? So 0 factorial is defined as 1. So I could have started my counter at 0. Okay, so I see the factorials, and the second power just means I've got an n factorial multiplied with itself. And the 2n quantity factorial means I've got 2n times 2n minus 1 times 2n minus 2 all the way down to multiplied by 1. Okay, so that's the factorials. Tell me that I'm going to test this series using the ratio test. So I'm going to tell you what I'm going to use right here. And in the ratio test, we have to form the limit as n goes to infinity of the an plus 1 divided by the an term. In the an plus 1 term, I've got to replace each n with n plus 1. So here's what that would look like in this example. I would have 2 times n plus 1, then factorial. On the bottom, I'm going to have a pair of n plus 1 factorials. That's the an plus first term. Each n is replaced by n plus 1. Then I've got to divide by this. So I can waste time and put that fraction down here, but I know in my next step, I would take that fraction and flip and multiply it. So I'm going to go ahead and skip a step. I'm going to put the reciprocal of this over here as the product. Is that okay with everybody? Now this guy in here, if I distribute the 2, becomes 2n plus 2 factorial. and then put the other stuff around it. So we saw in the last example how n factorial and n plus 1 factorial cancel. This n plus 1 factorial is the same as saying n plus 1 times n factorial. And so with this one, 2n plus 2 factorial, what does that look like? If you were to write it out as a product, you start with 2n plus 2. What's it multiplied by? 2n plus 2 minus 1, which would be 2n plus 1. Then the next one? And then the next one? Which from the 2n on down is 2n factorial, right? So 2n plus 2 factorial is the same as 2n plus 2 times 2n plus 1 times 2n factorial. Agree? So that when I divide 2n plus 2 factorial by 2n factorial, those will cancel and leave me this. So this one divides that one out. So let me kind of put this in parentheses here. That one cancels with that and leaves me 2n plus 2 times 2n plus 1. Each of these will cancel. N plus 1 factorial is n plus 1 times n factorial. So when I cancel there, I'm going to have a factor of n plus 1 in the denominator. So I'm going to get one for that pair, and I'm going to get one for that pair. So I've canceled all of my factorials, and I just have a bunch of products there. You see how I did that? Did I lose anybody? Now, if you were to multiply that out, you'd have a second degree n on top and a second degree n on the bottom. So this limit should be the ratio of the coefficients. What will the ratio of the coefficients give you here? 4. You get 2n times 2n will give me a 4n squared divided by 1n squared. This limit should be 4. So let's go back and look at what our conclusion would be in the ratio test if the limit is bigger than 1, then our series diverges. So that's bigger than 1, our series diverges. So I'm going to make a note here that the ratio test does not work well in sums. For instance, if I were going to try the ratio test on something that we would clearly use a comparison test on, say n squared over n cubed plus 1. That one's real easy to use either the ratio, the comparison test with 1 over n, a limit comparison test, or an integral test. Either one of those are real easy. But let's play dumb and see if we can use the ratio test. Even though I told you right above it does not work well, we should get a limit of 1. So here goes the ratio test. We take the limit as n goes to infinity of an plus 1 over an. An plus 1 is that entire series rewritten, where each n is replaced by n plus 1. Then I got to take that and divide it by the series as I see it. So if I divide that by n squared over n cubed plus 1, I would flip and put the n cubed plus 1 up here and the n squared down there. Even if I multiplied everything out, nothing will cancel because I can only cancel through a product. So I eyeball this limit. If that's multiplied out, I get an n squared, and I multiply it with that, I get an n to the 5th. Both of them with a coefficient of 1. If I multiply that out, I'll have a highest power of n cubed times an n squared, another n to the 5th with a coefficient of 1. Nothing cancels. The degree on top is the same as the degree on the bottom. The coefficients on top are the same as the coefficients on the bottom. Every single time, unless your algebra is really screwy, you should get a limit of 1. The ratio test has a limit of 1. You get no conclusion. Okay? So no conclusion. These kind of things with sums in them best lend themselves to comparison test. We can compare to the sum, say n squared over n cubed, which is the sum 1 over n. 1 over n is a divergent p-series. We do the limit comparison test because we take the limit as n goes to infinity of the a-n's over the b-n's, the given over the lookalike. And so I would take the limit as n goes to infinity of n squared over n cubed plus 1, divide it by 1 over n, and I'd get an n cubed over an n cubed. I get a limit of 1. Any positive finite limit in the limit comparison test says both series do the same thing. My bn's diverged, so my an's diverge. So don't try a ratio test on things that are added. Only factorials and junk like that. If every single term in your series is in a product and has an nth power, the ratio test will work, but there's a quicker version of it called the nth root test. Let me write that one down and show you how it works. I thought you said I'd be done with 2 pages. Now I gotta go get another page. What's up with that, you guys? Remember the days when you had 50-minute classes 3 days a week? Wasn't that nice? What the heck made these 2 hours long? Nth root test. Works good. Let's say it works well. Let me use proper English. For a series in which everything is raised to the nth power. Then what we do is we take the limit as n goes to infinity of the nth root of the general term. And we'll get some number L with the same three conclusions as the ratio test. If L is smaller than 1, the series converges. If L is bigger than 1, the series diverges. If L is equal to 1, I don't know. So not just I don't know, we'll try something else. I don't like that one. Let's see if I have one that I like better. Let's take the sum from k is equal to 2 to infinity of 1 over the natural log of k to the k. The ordinary ratio test would work because you'll have a k plus first term over a kth term. Powers cancel nicely. But I'll go ahead and do the root test because it's quick and painless. We're doing the kth root test, since I used a k this time, where I take the limit as k goes to infinity of the kth root of my general term. So any root of 1 is just 1. Kth root of natural log of k to the k gives me natural log of k. As k goes to infinity, what happens to the limit of 1 over the natural log of k? It's 0. 0 is smaller than 1. So the series converges by the root test.
It's not converging to 0.
Nope.
It's not that.
If that's not what that means. It's just an indicator. Okay? All right, let's stop there then, by gosh. Let's stop there. That's section 8.5. I'll have to take a peek at web work and see if I got up there. I've got a bunch of tests. If you weren't here to get your test back last week, I've got them up here if you want your exam back. So stop by my desk and I can dig it out of here for you. Everybody at home? My home crowd here, you guys doing okay? Does anybody want to say anything? Chat. What's that? Uh-oh, there's 2 chats. Where'd they go?
We did that a full screen.
I'm thinking you're okay then. I'm gonna start recording here. And then we'll stop sharing here. If you guys are good, I'll let you guys go at home as well, if anybody's still awake. I hope to see you in class soon. Stop that share. And the session for everybody. All right, thank y'all. Thank you very much. Cut me off.